Now we're going to talk about the analysis of random mappings. This is something we've been promising for a while, and actually it uses a lot of the things, pretty much everything we've talked about so far for the analysis. And it's a very elegant and compelling application of analytic combinatorics. So a mapping is a function from the set of integers from 1 to n onto itself. This is from lecture 2. And we can represent every mapping with the digraph where every node has out degree 1. There's an arrow from every node to some other node. And the in degree could be anything from 0 to n. And the mapping divides up into components, and the components are cycles, or they're cycles of labeled trees. And there's lots of applications where we're interested in studying properties of mappings. And natural questions that come up are, how many different components are there on average in a random mapping? How many of the nodes are on cycles and how many are on trees? And so forth. And there's several other parameters that come up. And these are all handled in a fairly straightforward manner with the schemas that we've been considering. So first question is enumeration. How many mappings are there of length n? And we talked about this in lecture 2. In one sense, it's easy. You're mapping n integers onto themselves for each of the n position, each of the n nodes. There's n possibilities of where it could point, so it's n to the n. But the internal structure is of interest in plenty of applications, so this is another way to break out the number of mappings. And with analytic combinatorics, we're going to take a look at the structure, and that also allows us to analyze average values of parameters. And so we looked at this basic setup in lecture 2. It starts with trees, Cayley trees, labeled rooted unordered trees. A Cayley tree is a node and a set of trees, a root and a set of trees, and that translates by the symbolic method immediately to C of z equals E C of z. A component in a mapping is a cycle of trees, so y equals a cycle of trees, where C is the class of trees. So y is log of 1 over 1 minus C of z, where C of z is defined that way. And then a mapping is a set of cycles of trees. It's a set of mapping components. And that translates to the EGF equation, e to the log of 1 over 1 minus C of z, or 1 over 1 minus C of z. So that's the basic structure of the symbolic method for mappings. And now we're going to see how that has implications for the analysis of the enumeration of each one of these items and for enumeration of parameters of mappings. This is from earlier in this lecture. We just did this one. That's Cayley trees, labeled ordered trees. We went from the construction to the generating function, and then it's a simple variety of trees, so we went immediately to the coefficient asymptotics. That was our last example of a simple variety of trees. It's exactly this class C. But remember at the beginning of the lecture I pointed out that we not only can get coefficient asymptotics from singularity analysis, we can also get approximation to the function. So I've been leaving this off, but that's in the theorem. We get approximation to the function. It's lambda minus this same constant times square root of 1 minus z phi prime of z. So in this case, where lambda is 1 and they're all e, it says that the generating function for Cayley trees is asymptotic to, at 1 over e, which is where the near singularity of the origin is, it's asymptotic to 1 minus square root of 2 square root of 1 minus ez. And so we can make use of that approximation later on in the analysis. So for example, we want to know the number of cycles of trees. That's the components in a mapping. The generating function equation we get is immediately log of 1 over 1 minus C of z. But the last slide, C of z is asymptotic to 1 minus root 2 square root of 1 minus C of z, 1 minus that is root 2 square root of 1 minus EZ. So that comes out to half log of 1 minus EZ minus log root 2. Just plugging that in. So that's approximation to the generating function for the number of mapping components. But this one is just standard scale, just says log of 1 over 1 minus EZ is E to the n over n. So that immediately gives the asymptotics of the coefficients, or number of cycles in trees, is E to the n over 2n. Or another way to look at that is to apply Stirling's formula, get square root of pi over 2n n to the n. So that's two different expressions for that, or that's factoring in the n factorial to get the number of different mapping components of size n. So that's cycles of trees, and now we want the class of all mappings. So mapping is a set of cycles of trees, so that's e to the y of z. Y of z, on the previous slide, we show that y of z is asymptotic to half log 1 over 1 minus z, ez minus log of square root of 2. So now we have e to the log, that's x log. So our theorem for x log label sets says if we're taking e to something that can be approximated to a log, we just have to know the constants. Coefficient of the log is 1/2. Z over rho, that's 1 over e, and beta is minus log 2. So those three values, plug those in, and we immediately get the asymptotics of the class of all mappings. Alpha equals 1/2, beta equals log square root of 2, rho equals 1 over e, and we get the number of mappings is asymptotic to n factorial e to the n over square root of 2 pi n, which is Stirling's equation in another form. It gives, applying Stirling just leaves the n to the n, and that's what we're looking for in the first place. Even the three simple transfers from analytic combinatorics, that seems like a lot of work to get down to n to the n, but it tells us the entire structure, and we can extend this to similar problems as well. I just want to give an overview of what that structure looks like. Just a reminder again, we started with Cayley trees, and we applied our simple variety of trees schema to get that one. And then for components and mappings, we plugged in that approximation and used the standard scale. And then to do mappings themselves, we use xblog. So three different transfer schemas to get down to the answer for mappings. And so they all have their uses in this problem. But more generally, if we want to look at problems like what's the average number of components in a random mapping, or how many of the nodes are on cycles in average, and these are calculations for the small examples, then we can get those just by the same process, just extending the transfer theorem slightly. Well, components come for free because we have the corollary to xblog, saying that if you have an xblog setup, the number of components is alpha log n, and we had alpha equals 1/2, so average number of components in a random mapping is 1/2 log n. Again, that comes immediately through by the same process that we use for a simple problem like permutations. Or nodes on cycles, well, we can use bivariate generating functions. Mark the nodes on cycles with u. So then we get a bivariate generating function, xblog 1 over 1 minus u. And now we can put in, to get the expected number of nodes on cycles, we have to differentiate with respect to u and evaluate at 1. So that gives us an expression in terms of the generating function for Cayley trees. But now at this point, with singularity analysis, we have an approximation for that generating function, so we can plug in that approximation. So c of z equals 1 minus square root of 2 square root of 1 minus ez. 1 minus c of z equals just that, and then if you square it, you get 2 times 1 minus ez. and C of z over 1 minus C of z squared is asymptotic to 1/2 1 over 1 minus EZ. So you can check that, but that's not too difficult. So that gives us an approximation for the generating function for the expected number of nodes on cycles, and we want to get the coefficient of z to the n in that, but that's just an expansion. It's just e to the n over n to the n. And then applying Stirling formulas, the pi comes back, pi over square root of 2 pi comes back. And so the average number of nodes on cycles is square root of pi over n over 2. Very straightforward calculations based on singularity analysis. And this graph, for example, it predicts that there'd be 12.5 nodes on cycles, and actually there's 9, and that's for bigger graphs it'll be more accurate. These estimates are accurate to 1 over n, and we could get more terms if we wanted. Because everything that we do is extendable to any asymptotic accuracy. So that's the use of singularity analysis to study mappings and their characteristics.